And I'll do the usual share screen. Hopefully we can work this out without any trouble. So let's do this. All right, good. If this starts to gradually darken as my lecture proceeds, would somebody tell me about it, and I'll try to lighten it up again. But this is a pretty good, by my screen anyway, it looks like a pretty good contrast to what I want. So I want to start tonight by going over some items that came up in previous lectures, and I'm not actually sure that I made these points. So I want to go back and make sure I really covered it. Maybe 2 or 3 lectures ago, we were talking about the states of the electromagnetic field that had 1 photon and 2 photons, et cetera, and how they can be associated with wave functions. So for example, psi 1 here stands for an arbitrary single photon state of the electromagnetic field. And the idea is you apply a creation operator to the vacuum. This creates a single photon. This is using this continuum normalization, so there's no boxes here, and k is a continuous variable. In any case, that creates a single photon, which is parameterized by the mode, which is mu and k. And then we multiply it by a complex function, f mu of k, to form linear combinations and sum on mu and integrate over k. And that gives us an arbitrary linear combination of these states that are formed by this creation operator in the vacuum, and therefore an arbitrary single particle state. So I hope you remember all of that. And we interpreted this f mu of k as a wave function of the photon. Now, if you have 2 photon states, then you apply 2 creation operators to the vacuum. One's got a mode mu k, and the other one's got mode mu prime k prime. So there's an unprimed mode and a prime mode to the vacuum. That creates a 2 photon state. And now we form arbitrary linear combinations of this, where the function now has to depend on both mu and mu prime and k prime. And we sum on the mu's and integrate on the k's, and it gives us an arbitrary 2 photon state. Now, the point that I want to make tonight, because it's important, and I was afraid I didn't make it in that earlier lecture, is this, is that all creation operators commute with one another. So these 2 creation operators can be swapped. And if they are, you see it amounts to just swapping the primed and unprimed mode indices. So if I swap them also in the F, then it returns the expression back to the original psi 2. It doesn't change under such an operation. What that shows you is that this function F might as well be symmetric under the exchange of the primed and unprimed mode indices. You have to change both the k value and the spin value mu in order to carry out the exchange. But it means it's unchanged under it means that only the symmetric part of this function f contributes to the answer. If you had an antisymmetric part, it would vanish because of the symmetry of this expression. So in other words, the wave function of a 2 photon state is symmetric under the exchange of the mode indices. And this is an indication that photons are bosons. And that was the important conclusion that I wanted to make. And so let me put that in here. Photons are bosons. Now, of course, you'd expect them to be bosons by virtue of the fact that their spin is 1. But the spin of the photon is a somewhat tricky subject because of the missing longitudinal polarization, which I touched on in not too much detail in a few lectures ago. In any case, it agrees with the usual rules, given that the photon is a spin 1 particle, and it should be a boson. This, what I've done here, is not a proof that photons are bosons. The only way you could prove that is to do it experimentally. But what it does show is that if you quantize a classical field using Dirac quantization, you're going to end up with bosons. And this is a consequence of Dirac quantization. And it means in particular that later on, when we come to quantize fermion fields, we're going to have a different procedure, because it won't end up, we don't want to end up with bosons. We don't want to end up with Fermi-Dirac statistics. So that was a point I wanted to make from a few lectures ago, and I wasn't sure I'd done it properly. Here's another point that I wanted to make. This comes from the very last lecture. I've got here a table of these matrix elements MBA, which occur in the spontaneous emission of photons. They actually occur in absorption and stimulated emission as well, but let's talk about spontaneous emission. We took this MBA, expression for which I haven't written down here, We expanded in powers of the fine structure constant, and we also separated it out into its different irreducible components. So we end up with a collection of irreducible tensor operators for each of the different the different multipole components. There's the electric dipole, the magnetic dipole, and the electric quadrupole, and they have the corresponding operators, the position vector of the electron, the L+2s of the electron, and the quadrupole moment tensor of the electron. These have different K values and different properties under parity, and these things affect the selection rules of the matrix elements. Now, something I wanted to draw your attention to, which I think I neglected in the last lecture, is that these also have order in the fine structure constant. The E1 matrix element, the MBA E1, is of order alpha to the 0. It doesn't say it's not small, it's of order 1 in atomic units. If you look at the formula for the MBA E1, here it is. The mass, the frequency, h bar, the polarization vector, and the position vector, assuming the atomic states are reasonably small quantum numbers, everything here is of order 1 in atomic units. So this MBA is of order 1, and if you want to list it in terms of the power of alpha, it's alpha to the 0. Now the M1 and E2, which I haven't written down the corresponding MBAs for them, but they were in the last lecture. If you look at them, they have a factor of the wave vector K in there, and as I explained in that lecture, the K is of order alpha, fine structure constant. The K of the light wave is a small quantity. So these two are down, the matrix elements are down by a factor of alpha compared to the E1. Now the Einstein A coefficient, the formula we derived is this thing here. It's some prefactors, and then there's the square of the matrix element. If the most easy way to analyze this is to go to atomic units. Atomic units would mean the electron charge E, the mass m, and h bar were all equal to 1. And it would mean that the speed of light is 1 over the fine structure constant. So if I do that with this formula here, what I get is at 4, I get an alpha cube that comes from the c cubed here. The omega is still there, and the MBA squared is still there. This is the MBA squared averaged over polarizations and angles. Well, in the case of the E1 transition, where the MBA is of order alpha to the 0, this means that the Einstein A coefficient is of order alpha cubed. So let me put AE here. This is of order alpha cubed for an E1 transition. Whereas for an M1 or E2 transition, the matrix element goes like alpha, so the square of it is alpha squared, and so these things go like order alpha to the 5th power. Both of them do, they're the same order of magnitude. If you go to higher multipoles, such as magnetic dipole, you'll find it goes like alpha to the 7th power, and so on. Well, alpha cubed is something like about 10 to the minus 6, and alpha to the 5th is about maybe 10 to the minus 11, very roughly here. Let me move it over so you can see. And so this is all now measured. What this means is if we measure in atomic units, then the rate at which we make a transition, an E1 transition, which is the fastest one, is of order alpha cubed. Well, a time which is of order 1 in atomic units is basically the orbital period of the electron. And so this means the transition rate is down by a factor of about 1,000,000. That means that if you're, for example, looking at let's look at the fastest transition in hydrogen. That would be, if I can do it down here, that would be from the 1s to the 2p to the 1s transition. This is what's called the Lyman alpha transition, and it's the most rapid transition. It has a wavelength of about 120 nanometers. Anyway, the Lyman alpha transition is the fastest one, and it means that what this calculation shows, this rough calculation shows you that the electron orbits in its orbit in the 2p orbit roughly about 1,000,000 times before it makes a drop into the ground state. That's how slow it is. If we were talking about an M1 or an E2 transition, then the number of orbits would be in the order of 10 to the 11th power before it made the transition. Much slower, as you can see, bringing it down into the microsecond range for the lifetimes. So the lifetime of an E1 transition is typically about, for Lyman alpha, it's somewhere in around 10 to the minus 9 seconds, about a nanosecond, 10 to the minus 9 seconds. That's about the transition rate, Einstein A coefficient for Lyman alpha, which is very roughly what 10 to the minus 6 is if we translate it from atomic units into seconds. So that was an important point that I wanted to make about about the transition rates. These transition rates are small, and on this atomic scale, and they are so because basically because of the fine structure constant is small. If you do problems of nuclear physics where you're studying radiative transitions in nuclei, such as in the iron 57 nucleus that we talked about earlier in the connection with the Mossbauer effect, or other nuclei, there's thousands of nuclei making with many thousands of different states. In any case, there's a whole industry to study them, and they have all kinds of multipoles, including higher multipoles that are important, and a very wide variety of transition rates. But in any case, in the case of nuclei, the suppression factor that comes from, is represented by alpha here, that applies for electromagnetic transitions, is actually not as favorable. So you don't get as strong a suppression on higher multipoles in the case of nuclear transitions. All right. In any case, those were some things that I wanted to say. I wanted to say some other things too. In case I didn't mention it, I want to mention this fact is that what's called the dipole approximation, which leads to the electric dipole multipole, that's why it's called the dipole approximation, is assuming that the K, or K times R, is much less than 1, where R is the position of the electron. This means the position of the electron is bounded by the atomic wave function, which is of the order of the Bohr radius. So K times the Bohr radius is much less than 1. This is true for optical transitions in atoms, and therefore even more true for infrared or longer wavelength transitions. On the other hand, if you wanted to get up into ultraviolet, far ultraviolet or X-ray range, then this would not be a good approximation. In any case, I just want to mention that that's the dipole approximation is simply replacing this phase factor by 1. It's a way of saying that the phase of the light wave is nearly constant over the extent of the radiator, which is the atom itself, a little antenna. Speaking of antennas, I'd like to begin a little bit of new material tonight by telling you some things about antenna theory, which is actually involved in some of these formulas I've got here. Let me pull this out and get a new page here. So here's a new page. Let me say some things about antenna theory. You know, an atom that's emitting a photon is actually a little antenna, and we treat it by quantum mechanics, but many of the things that you learn about antennas in classical E&M actually transfer over. A lot of the qualitative ideas do anyway. I want to say some things about that, and also about the Larmor formula, which is a formula from classical E&M. I'm going to refocus this here, so because the distance to the screen changed slightly. Okay, I hope that works. Let me start with the Larmor formula. The Larmor formula gives the power radiated by an accelerated charge. It's a standard calculation in Jackson's book, for example, to calculate this quantity. And it turns out to be 2/3 E squared A squared over C cubed, where A is the acceleration of the charged particle. So this is the standard formula for the power radiated by an accelerated charged particle, and it's a non-relativistic formula. It only applies when V over C is much less than 1. Now, let's suppose that the particle is moving, let's say, in a circular orbit, which might be a crude model of an atom, or maybe it's oscillating back and forth along a line, which is what would happen if you had an electron in a linearly polarized electromagnetic wave. The electric field would push it up and down in the direction of the electric field, and so the electron would oscillate at the frequency of the wave, and as a result, it would radiate its own wave. That's the scattered wave produced by the electron. In any case, in these two cases, the acceleration could be written as something like r times omega squared, where omega is the frequency of either the orbital motion or the oscillation, and r is either the radius of the circle or the amplitude of the oscillation. So this is just dimensional analysis on harmonic motion. So if I plug that in there, then what I get is I get 2/3 times E squared times R squared times omega to the 4th power divided by C cubed. If the amplitude is fixed, then the power radiated goes as the 4th power of the frequency. Now, the world of antennas is, okay, so let's see, here's one thing I want to point out, is that the electric dipole radiation via our quantum calculation is actually very close to the Larmor formula. And in order to see that, let's take this expression for the Einstein A coefficient, and for the MBA, let's put in the electric dipole version of the matrix element. That's these constants in front, the polarization vector dotted into the matrix element of the position of the electron taken between the initial and final atomic states. You can think of this matrix element as kind of an average position of the electron while it's making the transition from state A to state B, or a kind of an average of its position between the initial and final states. This is going to be just a rough calculation we're doing, an order of magnitude. So it's good enough to think about it that way. But if we do, then I can sort of replace this by minus m omega over h bar, and I'll skip the epsilon because it's of order unity. And just as an order of magnitude, I'll write it as like an average value of r, something like that. So let's take this then and let's square it and plug it in up there into this MBA and see what we get. So let me do this here on the next page. So what we want to do is it's going to be, we get the A Einstein then is equal to, I'll skip the 4 too, we'll just do an order of magnitude. It's E squared h bar omega divided by m squared c cubed times MBA squared, which is m squared omega squared divided by h bar squared times the average value of r squared, like this. So you can clean this up a little bit, and the m squareds cancel out, and you get e squared omega cubed over h bar c cubed times the average value of r squared, like that. So that's the Einstein A coefficient, at least as an order of magnitude from our calculation. Now then, to get the power radiated, we need to take the rate at which photons are being produced multiplied by the energy of the photon. So that's what the power is going to be. And if I multiply that through, I get E squared, as you see, omega to the 4th divided by C cubed times R squared, like this. So now compare that to what we got up here for the Larmor formula for periodic motion. And you see they're very similar formulas. They got the same structure exactly, but the radius of the classical motion of the particle is now replaced by some kind of average radius inside the atom. So the point of this is to show you this close relationship between the Larmor formula and electric dipole radiation in atoms. Now here's something else I want to tell you about basic antenna theory. There are two kinds of antennas. If you look at antenna theory, there's the large ones and there's the small ones. And the small ones are characterized by the fact, well, let's let L equal the size of the antenna. And I won't use R for it because I'm using it up here for other things. But anyway, a small antenna is one for which the size of the antenna divided by the wavelength is much less than 1. And a large antenna is where this ratio, dimensionless ratio, is comparable to or greater than 1. So this is kind of the world of antenna theory, is these two cases. The small ratio L over lambda, much less than 1, is the easy case. And so that's the one I'm going to talk about tonight. Let's look at this easy case. Now, if we have light waves in L over lambda, the lambda is, of course, as an order of magnitude, it's 1 over k. There's a factor of 2 pi in there, but I'm going to ignore that because we're doing order of magnitude estimates. And this is also the same thing as the speed of light divided by omega, multiplying both sides by c. Ck is omega. Yeah, c over omega. And so this then can be written as omega L divided by c, right? Omega L divided by c. L is kind of like well, as I said, it's the length of the antenna. Now, in the classical Larmor formula, if I consider the radius of oscillation to be like the length of the antenna, because that's kind of what it is, a single particle, I can take this Larmor formula, which is here, and replace this L by an R, so it's omega R over C. Let me factor out a factor of omega R over C, and I'll drop the 2/3. If I do, the power then becomes E squared, and then I get omega squared divided by single factor of C, and then I get L over lambda quantity squared. All right. Now, by the way, this L over lambda, if the L is identified with the radius R here, I can write this as omega, let me write as omega R over C, like this. Omega R for the harmonic motion is just the velocity, so this becomes V over C. So the small antenna limit for the Larmor formula is equivalent to saying that the velocity of the oscillating particle, which V over C, is much less than 1, which is to say that it's non-relativistic. So this is basically a non-relativistic formula. It's a small antenna non-relativistic formula. I'm gonna try to readjust this again to make it brighter. Good. All right, good. Do you think that's better? Does anyone tell me that looks better when I brighten it up, doesn't it? It looks better to me. Anybody, tell me if that looks better.
Oh, it does.
It does, good. All right. Now, this is for electric dipole radiation. And I kind of showed that this is equivalent to the E1, as an order of magnitude, this works for E1 transitions, where L would be the size of the atom and lambda is the wavelength of the light. But it also works for this classical Larmor formula. If you want to talk about quadrupole radiation, like electric quadrupole radiation, the power in that case is the same factor, E squared omega squared over C. That gives you dimensions of power, you see, that's the dimensionality part of it. But then you have L over lambda to the 4th power. So if it were non-relativistic, it's down by another factor of V over C squared, which in the atom means a factor of alpha squared. That's just what we saw, is that the E1 transition went like alpha cubed and the others went like alpha to the 5th, because they're down by, you know, another factor of V over C squared. All right. An interesting thing about this is that one thing I might mention is that if I take E squared, which of course is the coupling between two charged particles in electromagnetism, and I replace it by the corresponding coupling you'd have in gravity between two masses, M1 and M2, you need to put in Newton's constant of gravitation. If you plug that into this formula here with the same lambda over L over lambda to the 4th power, you get to within an order of magnitude. There's a constant in there that might be something like 3 over 30 seconds. I'm not sure what the actual numerical value is. But apart from this constant in here of just involving dimensionless numbers, you get the correct answer for the radiation of gravitational waves from oscillating objects. Gravitational waves don't have any dipole radiation. Quadrupole is the first multipole that they possess. So this is the formula to use. And you see how easy it is as an order of magnitude to get that answer for the power radiated. By the way, if you then combine this formula for the power radiated for the energy contained in an elliptical orbit using just Kepler's laws, it's easy to calculate a formula, to produce a formula to show how the energy of the orbit decreases as it radiates gravitational energy, and therefore the orbit shrinks and the frequency goes up, and you can obtain a formula for the frequency as a function of time. And this gives you the envelope for these chirp functions, in case you've seen them, in these LIGO detections of gravitational waves. You know, it oscillates up and down, increasing amplitude and decreasing frequency, and then boom, and then it's done. Then it goes over the event horizon and it's done. What happens when you get to the event horizon is that all your formulas based on Kepler's laws are going to break down, because it's now really general relativity. But at the same time, what's happening is the V over C parameter, or if you will, it's the L over lambda, either one, they're the same thing. This is approaching 1. And in other words, the two orbiting objects are approaching the speed of light and orbiting each other as the event horizons cross. And that's the end of the chirp. But it's a fun little exercise. It only involves elementary mechanics to, 105 type mechanics plus this kind of analysis to get that. All right, so those are some elaborations on this radiation problem, or the interpretation of the emission of radiation from atoms and a quantum treatment of it in terms of antenna theory and connecting it with classical theory. Are there any questions about that before I go on? Because basically or anything having to do with the emission and absorption of radiation, because I'm ready to go on to a new topic now. No questions. Okay. All right. Then let me move on to the new topic, which is going to be the scattering of radiation, which will take us the next lecture and a half or so. We're going to study the scattering of radiation by material systems, but to make the analysis simple, we'll make our material system a single electron atom. At some point that could be interpreted as hydrogen. The formalism, however, is easily modified to handle other systems. And even restricting it to hydrogen, the answers you get give you an idea of what happens, at least as an order of magnitude, for dealing with transitions of any atom of valence electrons, at least, and typically what happens in molecules or in solids when you've got transitions amongst valence electrons. So it gives you a very good idea of what happens for other more complicated systems. Basically, what changes with the other systems is that the matter matrix elements become more complicated, but the rest of the story involving the photon modes and everything else stays the same. So here's what we're going to do. We're going to consider an incident photon gamma. Let's call it gamma stands for a photon coming in. It hits an atom. Let's say it's in state A. And by the way, I've been intending to. I want to use this other pen, which I'm trying to discipline myself to write with a pen with a thicker point, because I think it forces me to write it bigger, and I think hopefully makes it easier for you to see. In any case, so far tonight I've been using the fine pen, but I'm switching to the duller point now. Anyway, so you hit an atom in state A, and as a result, the atom may make a transition to a different state B, and a new photon, let's call it gamma prime, is emitted. And of course, there's some angle between the photons, which is like a scattering angle. So you see, this can be regarded as a scattering of a photon by an atom. It can either be an elastic scattering. It would be elastic scattering if the final atomic state B is the same as the initial one, and it's inelastic otherwise. It's inelastic if B is not equal to A. If B is equal to A, then the energy, let's call it omega prime, or the frequency omega prime of the outgoing photon is equal to that of the incident photon just by conservation of energy. Here, by the way, I'm assuming the atom is infinitely massive, and the recoil of the atom can be neglected. For optical frequency photons, that's an excellent approximation. But if you're going to do more high energy photons, gamma rays, and so on, then you better take into account the center of mass degrees of freedom also. Well, in any case, let's just make our atom infinitely massive. So we're going to be mainly thinking about optical range or lower frequency. Infrared would be fine too. A range of energies of photons in the following analysis. All right, if B is not equal to A, then the omega prime, which is the frequency of the outgoing photon, is related to the frequency of the incident photon minus omega BA, because you have to account for the energy that was needed to lift the atom from state A into state B. That's assuming state B is higher in energy than state A. By the way, the final state after the photon has been scattered could be either higher in energy or lower in energy. Not if A is the ground state, of course, you can't go to any lower energy. But if A were an excited state, you certainly can make transitions to lower energy states, and this happens. This happens, for example, in Raman scattering, which I'll say something about a little bit down the line. All right, so that's the basic setup. If I write this as a reaction, it's going to be gamma plus A goes to gamma prime plus B. And I'll let gamma, the incident photon, have mode lambda, which otherwise is a shorthand for K mu. And I'll let the final photon gamma, scattered photon gamma prime, have mode lambda prime is equal to K prime mu prime. So the modes of the incident and final photons are, well, the mode of the incident photon is fixed. The mode of the final photon will have to compute transition probabilities and then sum over them to get cross sections. You'll see. In fact,
Professor,
yes.
can I ask a question? I just think that maybe this is easy, but I just never saw it. Why is it the names elastic and inelastic, and are those related to what we get taught on in like 7A?
I'm not sure what you get taught in 7A, but it's called elastic if B is equal to A because the state of the atom didn't change. And that means that the energy of the outgoing, just by conservation of energy, the energy of the outgoing photon has to be the same as the energy of the incident photon. That's this omega prime equals omega. So it's like it's an elastic bounce, of a ball. It comes off with the same energy that it went in with. Whereas if you change the state of the atom, then some of the energy of the photon was used to lift the atom from state A into state B. That's assuming B is higher than A. It could work the other way too. state B might be lower in energy than A, in which case the scattered photon has a higher energy, gained energy. That can happen also. Does that answer your question?
Yeah, yeah,
Okay.
yeah, it does. Thanks.
And I think this is the first time we've considered inelastic processes, although maybe we had it a little bit with the spin flip. The spin flip, a homework problem. The spin flip didn't involve any energy change because the final energy in the asymptotic region does not depend on the spin of the electron. There's no magnetic field out there, but nevertheless, that was an example of an inelastic, possibly inelastic collision, because it could change the state of the. Well, there was a state of the target particle. Here we're changing the state of the incident particle. This is really a two-particle system we're dealing with here. All right. In any case, let's just use the notation that the unprimed mode is the incident mode and the prime mode is the scattered mode. All right, now we're going to use time-dependent perturbation theory to analyze this. So to remind you, in time-dependent perturbation theory, we had a kind of a general notation that we used in which I was the initial state, which is supposed to be an eigenstate of the unperturbed Hamiltonian. And we use the symbol n to stand for a variable final state that we typically summed over. We also use the symbol k to stand for an intermediate state, which I'll say more about that about the intermediate states in a minute. But for this problem, the initial state is going to be one in which the atom is in state A. And as I've done before, I'm going to use capital letters for atomic states or matter states. And so the atom is initially in state A, and the field is in the state lambda. That's to say, there's one photon in mode lambda. We can also write this way, and then A lambda dagger applied to the vacuum. That's another way of writing it. And I'll also write it this way: it's just simply A lambda. There's a lot of ways of writing this. Likewise, the final state is one in which the atom is in state B, and we have a photon in mode lambda prime. This can be written as B, and then we've got A lambda prime dagger applied to the vacuum. And this can also be rewritten as B lambda prime, like so. Now then, we also know that in time-dependent perturbation theory, we need this frequency omega ni, which is the Einstein frequency connecting the initial and final states. This is what goes to zero to enforce energy conservation. This is the final energy En minus the initial energy Ei divided by h bar. The initial energy Ei is equal to the energy of the atomic state A plus h bar omega. And the final energy, En in this case, is equal to EB plus h bar omega prime. And so this is equal to omega prime minus omega minus omega BA. No, it's plus omega BA, plus omega BA. The initial energy is equal to omega prime plus omega BA. All right, so this is the omega Ni for this problem. All right. Now, let me remind you of some things about first order time-dependent perturbation theory. We had a transition amplitude Cn of t, and it was defined as the matrix element of the evolution operator in the interaction picture, which we call W of t, between the initial and final states. And we expanded this in powers of the perturbation. The initial term is a Kronecker delta connecting the initial and final states, because all the probabilities in the initial state at t equals 0. And then we had first order and second order and so on contributions to the transition. This is a transition amplitude, not a probability. Expand the transition amplitude like this. And the Cn at first order in time-dependent perturbation theory was, it turns out to be this formula. There's a somewhat complicated looking time-dependent factor. It's e to the I omega ni t over 2 times sine of omega ni t over 2 divided by omega ni. And then this has been multiplied by the matrix element connecting the initial and final states, which is taken in the Schrodinger picture. This is our formula for the first order amplitude. This factor that I put into square brackets here is a characteristic time-dependent factor that occurs here. And this is a factor that when you square it in order to get the probability at first order time-dependent perturbation theory, this is for the case where n is not equal to I because I'm ignoring the Kronecker delta here. Then this gives us something can be written this way as 2 pi times time divided by h bar squared times this function delta sub t of omega ni times the square of the matrix element. This is what we got in time-dependent perturbation theory at first order, where this pseudo delta function, delta t, turns into a Dirac delta function if the time is long enough. And we went through this in some examples, including an example involving scattering theory. Scattering theory we dealt with before was a scattering of a spinless particle by a potential. Now we're scattering photons. We'll see there's some similarities between these two types of scattering problems. All right, so this is a little bit of a review, and we've calculated the omega ni, which is going to be needed for this formalism as we see here. Well, the next thing to do is to write down the Hamiltonian we're going to use. I'm going to call the Hamiltonian either K or H, depending how I feel about it. In the case of K, we'll write it as K0 plus K1 plus K2. And here are the terms of K0. K0 is going to be P squared over 2m plus the potential for a single electron atom, I'll call it U of R, plus the free field Hamiltonian, sum on modes lambda, H bar omega lambda, A lambda dagger, A lambda, like so. And if I haven't said so yet in this, I'm going to be using box normalization in all of this because it's a little simpler than trying to do it otherwise. So this is a discrete sum, then we're summing over the discrete modes of the box. The K1 is equal to E over MC times the momentum P dotted into the vector potential evaluated at the particle position, plus the spin S dotted into the magnetic field evaluated at the particle position, like that. And the K2 is equal to E squared over twice MC squared times the vector potential A evaluated at the particle position R quantity squared. These momentum term, this P dot A and this A squared term come from the expansion of the kinetic energy in the matter Hamiltonian, part of the Hamiltonian. The S dot B comes from the mu dot B term of the interaction of the electron with the magnetic field. And to remind you again, this A and the B here are now quantized fields, the quantum field, which we usually write as a Fourier series in terms of A's and A daggers that provide the coupling to the electromagnetic field. So this is the Hamiltonian setup. Now, as far as this H notation is concerned, I'm going to write this as H0 plus H1. And H0 will be defined to be the same thing as K0. And H1 will be defined to be the same thing as K1 plus K2. I want to write it this way because this K2 is actually of higher order than K1 in the small parameter here, which is basically the vector potential or the magnetic field. And so there's two different orders. There's a mixing of orders here in this breakdown of the expansion of this K Hamiltonian. And it's convenient to have a single symbol for the entire perturbation, K1 plus K2. That's why I'm writing it like this. Also, when we did time-dependent perturbation theory, we just had an H0 and an H1 and not an H2. So that's another reason for doing it, to relate it to the formulas we worked out earlier with time-dependent perturbation theory. All right, so that's kind of the setup of the problem then, and the rest of it is to work it through and to see what new techniques we need to do that. The first thing to say is that let's look at let's look at it in terms of C1, first order time-dependent perturbation theory. We need to calculate the matrix element of H1 between the initial and final states. I think the initial and final states I had listed up here, a few lines up. Here they are. The initial state is A lambda and the final state is B lambda prime. So what I'm calling in a general notation, this matrix element in H1I, which appear H1, that's an H1I, which appears in time-dependent perturbation theory, is to be understood for this problem to be a B lambda prime on the left, and in the middle is K1 plus K2. And then on the right, we've got an A lambda, like so. Okay. Now, as I just mentioned, K2 is of order the vector potential squared, whereas K1 is of order the vector potential of the first power. So for our first stab at this, we're going to ignore K2 and just concentrate on the K1, in which case this just becomes, let me write it this way, is B here. I'll have the vacuum 0. I'll have the annihilation operator A lambda prime on the left. That's the B lambda prime written out more explicitly. And then for the K1 is going to be, it's basically P dot A So the K1 is going to be a Fourier series for the vector potential. Let me write it this way, involving an A lambda and an A lambda dagger, like this, with bunch of constants and stuff in there, which I'm suppressing, like this. And then the A lambda state on the other side is atomic state A, and then I have an A lambda dagger creation operator applied to the vacuum. So this is going to be the structure of this matrix element at first order perturbation theory. If we just look at the field part of it, we have the vacuum bra there and the vacuum ket there. We've got an annihilation operator there, a creation operator there, and in the middle we've got a choice of either a creation or annihilation operator. Oh, by the way, something I forgot to mention. I got to be careful here. I don't want to just sum on lambda, because lambda was our designation for the incident photon, the mode of the incident photon. So it's not a variable of summation we want to use here. Let's call it lambda 1 here. That'll keep it distinct from the lambda prime, which is the final mode of the scattered photon. We call it lambda 1. In any case, you see this is the structure of this matrix element. So this is an excuse for me to say some things about vacuum expectation values of products of A's and A daggers, which occur in this business. And to present some general rules for such matrix elements. These can be put in any order. These occur in practice in all kinds of different orderings. They don't have to be ordered A's first and A daggers second. In any case, the A daggers, of course, create photons. Applied to the vacuum, they create photons. And the A's annihilate the photons. So if the number of A daggers and the number of A's are, let's say if the number of A's and the number of A daggers are not equal to each other, then when you end up applying these two things, you're always going to end up with a state which is, well, if there were more A daggers than there were A's, it's possible to annihilate all the photons, and then you annihilate the vacuum and the result is 0. If there's less A daggers than there are, less A's than there are A daggers, then you create a certain number of photons and you only annihilate some of them. And so what's left over is a state still with some non-zero photons in it. If that's the case, you get a state which is orthogonal to the vacuum. And so the result is this thing is equal to 0 unless the number of A's is equal to the number of A daggers. And in particular, the total number must be even. Must be even, or else the answer is going to be 0. So this is a simple rule for seeing, it's kind of a selection rule for seeing when such matrix elements vanish or not. Well, let's go back to this matrix element we have here for H1. You can see that you've got 1 on the side and 1 on the other side and 1 in the middle, which could either be an A or an A dagger, doesn't matter. The point is there's three of them in here, such operators, and therefore this entire matrix element is 0. And thus we conclude that for this scattering process, the leading term, which comes from K1, sandwiched in initial and final states, vanishes. And therefore it will be necessary to go on to second order time-dependent perturbation theory to analyze this problem. And so that's the problem we turn our attention to now. Are there any questions about this up to this point? Up to this point, I think it's straightforward. It's interesting because it's novel, but it's straightforward on what we've done so far. All right. If no questions, then I'll proceed. So we need to go back and review time-dependent perturbation theory. I already gave you some of the main formulas here. Here's the transition amplitude with a Kronecker delta plus these states here. By the way, regarding this Kronecker delta, in our scattering process up here, we're going to assume that mode lambda prime is not equal to mode lambda. We'll assume this because otherwise you don't have any scattering. If the outgoing photon was in the same mode as the initial photon, then there was no scattering. So we're going to assume this. And that in turn implies that in the time-dependent perturbation theory, that the final state N and the initial state I will be distinct for this application. And so that term will go away. We also just showed that the C1, at least coming from K1, that's also 0. So we need to go on to C2. We need to talk about C2. So let's talk about C2 then. So here's what we got from here's it is. Let's do it right. Cn at second order of time-dependent perturbation theory is a function of time. If you return to the Dyson series, here's the formula we got. It's 1/IH bar squared. integral 0 to t dt prime, integral 0 to t prime dt double prime. And then we had the matrix element in H1 interaction evaluated at t prime, and then H1 interaction evaluated at time t double prime in the initial state I. Now, we adopted the strategy of converting this interaction Hamiltonians to the Schrodinger picture Hamiltonians. And in order to do that, it's convenient to insert a resolution of the identity, sum on KK like this, where these states K are called intermediate states between these two H's. And then we get a product of two matrix elements. And then when we convert that into the Schrodinger picture, this turns into the following. It's a sum on K, intermediate states. We have a phase factor e to the I omega n K times T prime times a matrix element in H1K. And then I'm not to run out of space. And then another phase factor, which is e to the I omega Ki times T double prime times the matrix element K H1I, like so. Hope you can see all that. And so what I propose to do, so that's the formula. So what I propose to do now is to do the T double prime integration. Here, let me get a red pen in case I'll do the T double prime integration. And that the only thing that depends on T double prime is that phase factor there. So if I do this, this turns into 1 over IH bar squared. The first integral is still here, integral 0 to T dt prime. And then we get the sum on K. And I get this phase factor hasn't changed, omega nk T prime. And now I'm going to write down the result of the T double prime integration. And that is this factor e to the I omega Ki T prime minus 1 divided by omega I times omega Ki. That's just an elementary integral to do. And then what's left over is the matrix elements in H1K, K, H1I, like so, second order. Now I can take these phase factors and multiply them together. And I'll take the denominator out, it's 1 over I omega Ki. And then multiplying this e to the I omega nk times what's in here, we'll note that omega nk plus omega Ki is equal to omega ni, because these are energy differences, En minus Ek plus Ek minus Ei. So this is a simple identity. And so this thing that I've underlined here turns into e to the I omega ni T prime minus e to the I omega Ki T prime, like so. And now we can do, okay, so we get these two phase factors here, and now we can do the T prime integration. Let's do the T prime integration. And you see there's two terms here. Let's call it term 1 and term 2. Let's take the two terms. So the term 1 then is equal to 1 over IH bar squared. That's still there from the leading thing here. The sum on K is there. We have the 1 over I omega Ki. Doing the integral of that first factor here, we get e to the I omega nit minus 1 over I omega ni. And then we get the product of the matrix elements in H1K, K, H1I, like so. And now the interesting thing about this is that this time-dependent factor that appears here is the same one that occurs in first-order time-dependent perturbation theory. Here I wrote it out in the square brackets in a more complicated form. But what's in the square brackets here is actually the same thing as in the round brackets here. If you factor this out, this becomes e to the I omega ni T over 2 times sine omega ni T over 2 divided by omega ni. This is a somewhat complicated time-dependent factor, but I'll remind you the important role that it plays in the theory, because when we square it, we get something which is proportional to time And what's left over is something that goes into a delta function. We divide by the time to get a transition rate, and then the delta function enforces conservation of energy. So many features of the theory depend on this factor. Well, in any case, this same time-dependent factor is now emerging from second-order time-dependent perturbation theory. Also, you may notice that this factor is independent of the index k, so this whole thing can actually be taken out of the sum, like so. And if we do this, then I'll go to a new piece of paper. Then this term number 1, which is a contribution to the second order to Cn2, is given by, I can write it this way, I can write it as 2 over IH bar times e to the I omega nit over 2. This is the same time-dependent factor, which I'm just copying again. Nit over 2 divided by omega ni. And then what's left over is a sum on k, intermediate states k, with starting with n h1 k, and then k h1 I, like this. And you have an energy denominator, which is ei minus ek. Okay? Same time-dependent factor as in first-order time-dependent perturbation theory. All right, now then, there's a 2 over IH bar there as well, which is also present in first-order time. See, here's the formula in first-order time. There's a 2 over IH bar there. Here's the rest of it. And then all that's left is the matrix element. So this is a contribution then to Cn at second order. Now, to go back then, what about the second term here? This term, if you can, this term does depend on the index k, and so it cannot be taken out of the sum. And when you square this, what you find is that it does not produce something that's proportional to time times an energy conserving delta function. Instead, what it does is it just gives you oscillations, oscillatory terms, so that when you divide by time, these bounded oscillatory terms go to 0 in the limit that t goes to infinity, which you want to do t goes long enough to call it infinity, to calculate a transition rate. And so these other terms labeled by number 2 here don't contribute to the transition rate. In fact, these other terms are transient terms, which disappear in the limit that t goes to infinity. We saw transient terms also in the scattering calculation we did for scattering by potential scattering. And the reason you have these transients is due to, it's basically the same reason we saw in that calculation. It's namely the artificiality of the initial conditions of this problem. Let me say something about those initial conditions. To go back to the original setup of the problem, which I've summarized here at the top of this page here, this is the scattering problem. We were assuming that the initial state of the system was one in which the atom was in state A, and there was a single photon in mode lambda. Well, single photon in mode lambda means that all of space is filled with a plane wave. That's the classical picture of it anyway, with an energy which is h bar omega. Now we're using box normalization, so there's h bar omega inside the box. In any case, you can visualize that plane wave. The problem is that plane electromagnetic wave is that perfect plane wave, including where the atom is located. Well, in practice, there's no way to get such a wave that looks like that in the location of the atom. You could certainly send in something that's like a plane wave and let it settle down after a while, but the plane wave would then become distorted in the neighborhood of the atom. So realistic initial conditions don't look like this. And what happens in effect with our artificial initial conditions is that the parts of the wave, the initial state, the initial wave function, the photon wave function in the neighborhood of the atom, which are not realistic, they kind of get swept out after a while. And if you wait long enough, they move to arbitrary large distances and basically get radiated away. And then you approach the steady state. So those are why we have the transients. Now, the existence of transients in this theory has to be regarded as a defect of the theory, I must say, in both the earlier scattering calculation and the one we're doing now. It's a defect of this theory that you have to even mess with those things. Why? You don't really want them. And as I say, it's due to the artificiality of the initial conditions. If you wanted to avoid this, the way to do it would be to say, well, the initial condition is not one where all of space is filled up with a plane light wave. the initial condition is some kind of a light wave as a wave packet, which is separated from the atom. The atom is over here and this wave packet comes in. There's no overlap with them at all. And then it comes together and interact and the scattered wave goes out. That's the more realistic picture. But in order to treat the problem theoretically that way, we need to talk about wave packets and time-dependent problems and so on. Now, if you do all of that right, what leads you into is the theory of the S matrix. The S matrix is the right way to do scattering theory. But the S matrix, unfortunately for this course, I'm afraid I don't have time to go into it because we are short on time. So someday I'm going to write some notes on it, maybe even this summer, I don't know. But for now, I'm afraid we can't do that. The S matrix is tricky. It's very tricky mathematically. And the typical textbooks that purport to describe it write down a whole bunch of formulas that are absolutely incomprehensible, in some kind of hand wavy way of hoping that you'll understand it by reading their stuff. Schiff, for example, is terrible on this. Anyway, so
Professor Littlejohn, may I ask a
that's
question?
a little bit of a digression into the S matrix and the transient problem. Yes, go ahead.
Oh yeah. So in later places where you do scattering amplitudes, it appears as though people tend to wick rotate almost everything so that things converge. And you never see that happening in like regular quantum mechanics like this. So I was wondering like what would be the conceptual like wrongdoing if you were to for some reason.
Well, I'm not sure exactly wick rotating, but I'm introducing these I epsilons, which is I've explained is an artificial damping parameter. It's introduced in order to get the Green's function.
Right, and that all makes sense. But what I'm trying to get at is the fact that people tend to randomly just wick rotate things later on, and we never do that in quantum mechanics like the way you're doing it, which I think is the proper way. So I'm wondering, like, what's the conceptual jump?
Yeah, I think I need to talk to you more explicitly about what people do with wick rotation. I mean, a wick rotation is just an analytic continuation in time. And if you're going to do it, you need to ask, is it valid? Because it involves complex number theory and so on. It depends on the context. But
Okay,
yeah,
that's fair.
wick rotation is not the same as the I epsilon prescription. But the I epsilon is a way of making things converge. And in the theory of the S matrix, there's tricky issues involving the convergence. The problem is the formulas people write down don't have any meaning because they don't converge. All right. Anyway, people want to always write down the matrix elements of the S matrix in a plane wave basis. And the action of the S matrix on a plane wave, by the usual definition of the S matrix, is not defined. So that's the main problem. All right. Anyway, so that's a tangent that I don't have time to go into tonight. But in any case, using the formalism we're using, i.e. time-dependent perturbation theory, we deal with the transient issues by throwing this number 2 term away. It doesn't contribute to the transition rate in the limit. And what that means is the term that does contribute has the same time-dependent factor that we had in the first order theory. And so the result is that we get an effective, let me call it Cn effective as a function of time. And what is it? It's the same factor time-dependent factor that occurs in the first order theory. I've written it out at least 3 or 4 times tonight. Sine omega ni t over 2 divided by omega ni. And I'll put it in square brackets, the whole thing, to set it off. And then this is then multiplied times something else here. I'll put this in curly brackets to make it look different. We have the NH1I. This would be what we'd have for first order time-dependent perturbation theory. And now we have another term. This is sum on intermediate states K. It's NH1K, K, K, H1I divided by E sub I minus E sub K. Like so, okay? And if we square this to get the probability, Pn of t, then the square of the time-dependent factor turns into 2 pi t over h bar squared times delta sub t of omega ni times the absolute value of this curly bracket thing here squared, where this comes down from above. And so you see, if we just kept this first term here, we'd have exactly the same results as we've had before with first order theory. And this now gives us the correction in second order theory. There's actually a Green's operator hiding in here. That's where this energy denominator came from. This KK resolution of states over this EIEK is really a Green's operator. And this whole thing can be understood in a formalism that's connected with the Lippmann-Schwinger equation. Well, in any case, for our problem, we determined that the NH1, so our NH1I, I'll remind you, got converted into this, interpreted as B lambda prime on one side, and then the K1 plus K2. And then we had the A lambda on the other side. And the K1 we found term gave us 0. And so this NH1I is going to give us from the K2, it'll give us something which is of order of the vector potential squared, because K2 in fact was the A squared term in the Hamiltonian. As far as the term from second order time dependent perturbation theory, you've got H1s in there, but they're going to be interpreted as K1 plus K2. Both of them the same, they'll be interpreted the same. If I just take the K1 in here, then I've already got something which is a second order in A squared. So if I'm counting orders by the order of the vector potential, which is how we want to do it, because that's what makes this, that's really the small parameter here. Then the statement that we want to focus on is that for the H1 term, we just replace it by K2. Effectively, we take the second order Hamiltonian in first order time dependent perturbation theory. And in second order time dependent perturbation theory, we take the first order Hamiltonian K1 and ignore the K2. And so that means that what we really want then for our curly bracket is not what I've written up above, but rather this. We want N K2I plus the sum on intermediate states lowercase k, in K1 intermediate state K, another copy of K1, initial state I, divided by energy denominator EI minus EK. By the way, this energy denominator should also remind you of what we did in bound state perturbation theory. It's the same energy denominator, as a matter of fact. All right. All right, so this then is the setup for the actual calculation of the scattering, the scattering cross section.
I have a question.
Yeah.
Do we not need like a K not equal to I condition or anything?
No, because this, you mean the intermediate state? Oh, I
Right,
see.
yeah.
I see. You're worrying about what happens when the denominator vanishes.
Yeah.
Yes, and we're going to have to worry about that later on. What happens when the denominator vanishes? Yeah, yeah. I wasn't going to go into it, but since you bring it up, here's the honest truth about this. It is that the fact that we're using box normalization is really wrong. There's, I mean, on the face of it, there's nothing. It seems like there shouldn't be anything wrong. You'd let the box go to infinity. You ought to get the real universe, right? But the problem is that in box normalization, you assume periodic boundary conditions, and the real boundary conditions are not periodic. They're outgoing boundary conditions. And if you take that into account, the outgoing, what you get is an I epsilon in here. Because that's the outgoing boundary conditions from the Green's operator. And
I see.
and that regularizes this denominator in the case when the sum is going to run right over it. Sometimes it does and sometimes it doesn't. But when it does, the I epsilon, without the I epsilon, the result is meaningless. As a matter of fact, the integral, this sum will turn into an integral. It doesn't have meaning. But with the I epsilon, it is not only meaningful, but it's also defined. I mean, it's finite. It's well behaved.
So it really is just like the Green's function popping up again.
It really
in a
is
way.
a Green's function
Okay.
popping up in there. In fact, if I had you for an extra hour tonight, I wouldn't even take that long. I could easily tell you how the Lippmann-Schwinger equation can be applied here. It's just, you just take the H0, H1, and you just do the Green's function for H0, and you get it. You get this. This is really the second Born approximation coming out here is what this is. All right. There's a whole world of stuff out here in the scattering theory. It's very interesting things that go on. All right. So I don't have that much time left tonight, only 15 minutes. Let's do the work some of the work that's involved in actually evaluating this. Let's start with the N K2I. More explicitly, this is B lambda prime on one side, and then the K2, which it goes like A squared, it's the vector potential, A of R squared. There's some constants in front. And then there's the A lambda on the other side. This is the N K2I, like this, is equal to that. All right. Now let me analyze this. So let's write this as B for the atomic state, vacuum bra here, and A lambda there, A lambda prime there. This was the this is the single photon state as a bra. And then the A of R squared, each vector potential is 2 Fourier series. There's constants in front, which I'll ignore. And then we've got a sum on 2 lambdas. I better call them lambda 1 and lambda 2 so I don't confuse them with the lambda and lambda prime. And there's an A lambda 1 and an A lambda 1 dagger in the first Fourier series, and there's an A lambda 2 and an A lambda 2 dagger in the second Fourier series. And this then on the right-hand side, we've got atomic state A, and then we've got A lambda dagger applied to the vacuum zero. Now we'll use our rules that we'll work on the field matrix element first. Here's the vacuum bra on that side, and here's the vacuum ket on the other side. Here's an annihilation operator. Here's either creation or annihilation operators, 2 of them, and there's an annihilation operator. So we have a total of 4 of them, and that's an even number. So that's good for getting a non-zero answer, but the number of A's and A daggers have to be equal. So here there's 1 A and there's 1 A dagger. So of these 4 terms that come from multiplying out these 2 Fourier series here, there's only 2 that will contribute. You have to have an A and combined with an A dagger, that one combined with that one, or an A dagger combined with an A. Only those 2 products will work. And so there's 2 cases. If I just look at the vacuum expectation values, it looks like this. We've got a 0 A lambda prime from the outgoing photon state. Then let's take this A lambda 1 here. Let's take this one here, A lambda 1, and then we get an A lambda 2 dagger, and then we get an A lambda dagger and 0. Let's call this case 1 here. Case 2 is going to be a 0 A lambda prime on the left. And then I have an A lambda 1 dagger. And then an A lambda 2. And then an A lambda dagger. All right. Now, let's look at case 2 first of all. So in case 2, here's what we're going to do. Oops. Did your share screen disappear?
No,
Or
it's
just-
We still see it.
Okay, it disappeared from me. Okay, I brought it back. All right, good. So here's what we do to analyze this. Is we use the commutation relations. Let's take case 2 first of all, because it's a little easier. So in case 2, what we get is, if I use the commutation relations for an A and an A dagger, I get a Kronecker delta at first order. So I get Kronecker delta lambda 2 lambda. And then what's left over is the matrix element 0, A lambda prime, A lambda 1 dagger, 0. And then I get another term that I get from swapping the order of these 2. But when I swap the order of these 2, it puts the annihilation operator next to the vacuum. So the correction term is 0. That way I got rid of 2 of the A's and A daggers. And then likewise, I do the same thing for this. I got a second Kronecker delta. So I get Kronecker delta lambda lambda 2 times Kronecker delta lambda prime lambda 1. Excuse me. That's what I get for the second of these here. Likewise, if I go through a similar analysis for the first one, I'll find the first one gives me Kronecker delta lambda lambda 1, Kronecker delta lambda prime lambda 2. It's the same as the number 2, but we swap the lambda 1 and lambda 2. And so these are the field matrix elements that result from this K2. And that's what that means is that because of these Kronecker deltas, only one term of these two Fourier series gets picked out. And when we evaluate you can do the sum. You can do the sum on lambda 1 and lambda 2 now, and just single terms. So actually two terms. There's these 1 and 2 here. Allow me to do number 2 because I think it's a little bit easier first. If I now write, I can now go back to this and write this out in complete detail here. Let's get this here. Let's get the b lambda prime on one side, the k2 in the middle, and then the a lambda on the other side. I'll remind you that k2 is equal to e squared over 2mc squared times the vector potential A of r squared, like so. So this is equal to the prefactor e squared over 2mc squared for the k2. The Fourier series for the vector potentials each have these square root prefactors, and when I square them, I get a 2 pi h bar c squared divided by v. I square it because there's two copies of A. And let's work on case 2 here then. So in case 2 then, let's go back up here. In case 2, first of all, let's say lambda 1 is equal to lambda prime. So the lambda prime is the mode of the outgoing photon, and the lambda 1 is the, let's see here, case 2 here. The lambda 1 was the a lambda 1 dagger. This is case 2 here. It's the annihilation operator here. So what happens in case 2 is that I get this thing here. I get from the two Fourier series, there's 1 over the square root of omega, omega prime. Each has 1 over square root of omega, but there's 2 of them there. And then what I get is the I get the polarization vector epsilon lambda prime star times e to the minus I k prime dotted into r. And then from the second Fourier series, I get an epsilon lambda times e to the plus I k, this should have been a k prime, k dot r, like so. And I forgot something here. I should put in there the atomic state B, and on this side, the atomic state A. Now let's see if you can see that on the paper here. No, bring it out. So putting all the pieces together, I get that. There's still an atomic matrix element left. However, we're going to make the dipole approximation, which means we can throw away these phase factors. That obviously helps things a lot. What's left inside is a dot product of polarization vectors, and then simply, which is a C number, and then simply the scalar product of atomic states B and A. So what this thing turns into then, finally, is to copy it out in totality is e squared over 2mc squared, 2 pi h bar c squared over volume v from these various sources these factors come from, 1 over root omega omega prime. Then I get epsilon hat dotted into epsilon hat dotted epsilon hat prime star, like this. And then Kronecker delta BA. And I'm making an abbreviation here. I'm just calling epsilon hat as the same thing as epsilon lambda. And epsilon hat prime is equal to epsilon hat lambda prime, just a shorthand for these polarization vectors. In any case, this is what comes out for this K. This is term 2 only. Term 2 only. Term 2 only. All right. Now, if you go through the same analysis for term 1, you find it gives you the same answer. So this thing gets doubled, is multiplied by 2. And this is the contribution from the K2 matrix element. Now, somewhere here, I thought I had a summary sheet where I kept this. Well, this is sort of it here. This is a summary sheet that I prepared for these different terms. Let me focus this again. Oh no, that was wrong. What did I do here? Yeah, right. All right, let's get it going again. Okay. This is a summary sheet which I prepared for these terms. And here is this prefactor, which is common to all these terms, multiplied by the dot product of the polarization vectors in the Kronecker delta. And this is this first term. This whole thing is the term in K2I. That's what this whole thing is. This thing multiplied times that. And I'll get to the Feynman diagrams, probably not this lecture, but that's the Feynman diagram for that. All right. So that's the first part of this. So let's see if I can find where we are. Here is the amplitude we wish to compute. You can see what it looks like here. And you see we've just done this first part. Now we need to do this, the first order Hamiltonian taken in second order perturbation theory. For that we need these intermediate states. So let's look at this in K1K and then K1I, where the K here is the intermediate state. Let me copy this again because this is the structure we want to look at. Here, do it right. In, put this out of the way. In K1, intermediate state K, K1, initial state I. The final state N is the B lambda prime, and the initial state I is the A lambda. This is going to be summed over K, and there's a denominator here too. This is the structure of what we need to evaluate. Now the sum over K was a sum that came from a resolution of the identity in the perturbation theory. And so in principle, this needs to run over all the states of the atom as well as all the states of the electromagnetic field, of which there is a huge number because the number of photons can go from 0 all the way out to infinity. However, the initial state I only contains one photon. And the K1 operator, you recall it goes like P dot A. So it's just got one copy of the vector potential in it. And so it's got only one creation or annihilation operator, one or the other. And therefore K1 is capable of either increasing or decreasing the number of photons by one, but that's all it can do. And therefore the intermediate states, which are allowed by the nature of K1, really break down into only two cases. One case is where they contain no photons at all, and the other one is where it contains two photons. So let's pick this, call this case 1 and case 2. Case 1 and case 2 is where the intermediate state K has no photons. And then in case 2, the intermediate state K has two photons. So, all right, now, if the intermediate state K has no photons, let's write it this way as I, capital I times vacuum. That is to say, it's what I'll call an intermediate atomic state, but the field is empty. Whereas in the second case, the intermediate state is going to contain an intermediate atomic state with two photons in the field, and I'll come back to that case a little later. In fact, let me come to it now. In this case, we've got K is equal to the intermediate state A like this, and then we've got a vacuum like this, and it has two photons in it. One of the photons has to be the initial photon. That's the A lambda. There's an A lambda dagger there. That's what came from I. That's this lambda that appeared there. Because we're creating a second photon means we're not destroying anything. So we're only going to destroy. We're not destroying that initial photon. Now the photon that is created by this K1 has to be the lambda prime, the outgoing photon in the final state. Because if it were a different mode, then the K1 over here could only, again, can only add or subtract a photon, but you need to subtract you need to remove a photon because you need to destroy to get rid of the initial photon because it's not present in the final state. And so the result is that this K1 is going to act by this K1 must act by destroying the initial photon, and therefore the photon that's left over must be the final one. And so we must have an A lambda prime dagger applied there. That's what this intermediate state must look like in order to get a non-zero answer. Okay, with all of that, I'm out of time. Unfortunately, it means I've ended up right in the middle of a lengthy calculation, so it'll be a lot to summarize and to get our gears going again the next time we meet. But anyway, that's where we got. So are there any questions about that? Any questions? I think while I'm waiting for questions, I will stop share. All right, if there's no questions, then thank you for your attention, and I'll see you. Tonight is Tuesday. I'll see you on Thursday, and anyone who wants to drop in early, I'll tell you the rest of the story about Cummins and Einstein.